Okay, we got ridiculous results here, mainly because I didn't have a .8 in front of this. I had an 8, so all the numbers would be 1/10 as great. Also, I had 7.76 instead of 776 instead of 784 here, because apparently I can't subtract 16 from 800. Okay, I subtracted 24 from 800. I don't know why, but anyhow, that's what it was. So correcting all these numbers, which are very straightforward, we find that the potential energy, according to this integral, is negative 78.4 Newton centimeters at the 14 centimeter position, and negative 64 Newton centimeters at the 20 centimeter position. Okay? So what's the change in potential energy from the 14 centimeter to the 20 centimeter position? Well, you subtract this from this. That's going to be 64 newtons minus 78.4, minus negative 64 Newton centimeters minus negative 78.4 Newton centimeters, which is 14.4 Newton centimeters, which totally agrees with what you got when you did average force times displacement. Okay? And we wanted to say 0.144 joules, which is good, because that's going to be more convenient if you're going to actually do velocity calculations and so forth, okay? Now again, where do we get the 0.144 joules without having to go through all this? This is a linear function of length. When your position is 14 centimeters, when L is 14 centimeters, you got 0 tension. At 20 centimeters, well, you got 20 minus 14, 6 centimeters, times 0.8 newtons per centimeter, which is 4.8 newtons. It's a linear force that goes from 0 to 4.8 newtons, so the average is 2.4 newtons. You multiply that by 6 centimeters, you get 4.14.4 Newton centimeters, and you don't have to do all the integration. Okay? Now the big thing, and we just looked at it, is you've got a graph of U versus X. In this case, well, let's just say you got an abstract graph of U versus X, okay? So somehow U versus X does something. If you've got an X1, then you've got a U1. If you've got an X2, then you've got a U2, okay? Now this isn't a graph of the potential energy function. Here, this is a simple quadratic, and it's pretty much all negative, okay? At least in the realm we're working on. But this is a picture of how you use a U versus L. And you can always get U versus L by figuring out what you would take a derivative of to get the force function. If you got the force function, the antiderivative of that force function is your U function. And as long as your U function is fairly simple, it's real easy to figure out what the function would have to be for its derivative to come out to this, okay? Now for the magnet and the car, I've got no idea what that function is. I have no idea what that function is. I could use a little multivariable calculus with a whole array of dipoles, and I'd have to plug it into a computer algebra system. It'd be something that nobody could integrate, except numerically, and come out with a function that probably wouldn't match what the magnets are really doing anyway. The best we can do with the magnets is we have a graph of U versus L. It looks like this. So if I've got an X1 and an X2, I get a U1 and a U2, and I get my change in U, which is related to the energy by what we see over here, and we can't quite see. Just quickly. Now, I think got most of it. Anyhow, change of potential energy is equal to and opposite to the work done by conservative force. That's all we're doing here. Integrating to get the work done by conservative force, or taking average force times displacement. Change of potential energy plus a change in kinetic energy minus the work done by non-conservative forces on the system is zero. We made sense of that and make sense of the way the book expresses it. So there's your statement. Very simple statement. Change of potential energy, change in kinetic energy, and work done by other forces. Okay?